Hey guys, welcome to the fifth talk of the Chromatic seminar. So today's speaker is Grigory Taroyan from University of Toronto, and Grigory will be talking about the Adams Spectral Sequence, and also like there'll also be computations for MU. Right? So Grigory, please take it away.
Okay, thank you. So I just want to start from some general idea of what is an Adams spectral sequence. So there are several, I guess, approaches to setting up an Adams spectral sequence. One of them is very geometric and topological, but today I want to discuss sort of another view of this machinery, which exhibits Adams spectral sequence as an example of descent spectral sequence. So what is the setting? So consider a sphere spectrum S and spectrum, the Erlenberg-MacLane spectrum for mod B cohomology. And we obviously have a mod B Fourierish map between the sphere spectrum and the cohomology spectrum. And it induces a map in the opposite direction on spectra of this ring spectra. So you can think of it phenomenologically, or you can use some kind of spectral algebraic geometry to do this. But the idea is that we have this contravariant functor of a spectrum, which takes as an input a ring spectrum and produces some kind of a space. Then obviously MU, as is any other ring spectrum, or any other spectrum for that matter, is an S module, which means that it can be considered as a sheaf on this spectrum of the sphere spectrum. So we can pull this sheaf back along this dual to the Fourierish homomorphism, and we will obtain a sheaf on the spectrum of the Erlenberg-MacLane spectrum. I guess I feel kind of weird repeating the word spectrum all the time, but well, let's call it an Erlenberg-MacLane thing. Spectrum of the Erlenberg-MacLane thing. Yeah, and the idea of the Adams spectral sequence is to recover the information about the original sheaf from information about the pullback. So this is a very general idea, obviously, and it can be interpreted more generally in terms of a descent spectral sequence. So I won't go into too much detail, but the idea is that if you have some kind of notion of a descent, so for example, a magnetic descent, then you can try to recover information about some object over something that you sort of cover by using information about pullbacks of this object to elements of the covering. So many well-known geometric spectral sequences fall into this category. For example, spectral sequence of a covering, or spectral sequence of a covering, anything that has to do with check cohomology and stuff like that. So that's just a very general idea. So we pull back the sheaf on the spectrum of this sphere thing, and then we want to calculate homotopy groups of this sheaf MU using information about pullbacks of this sheaf to spectra of Erlenberg-MacLane thing and its iterated pullbacks, its iterated fiber products. So this is somehow very similar to Czech cohomology methods. And so concretely, this is done using the following construction. So we take a ring spectrum, a co-simplicial ring spectrum, which is constructed this way. So we take an iterated tensor product of the Erlenberg-MacLane spectrum with itself over the sphere spectrum, and we obtain a co-simplicial object, where a co-simplicial structure is induced by the multiplication. And this is co-augmented over the sphere spectrum post-simplicial spectrum. And we have, thus we have a map from tensor product of X with the sphere spectrum into the totalization of this post-simplicial object. So if the spectrum X is sufficiently nice, this map is also sufficiently nice, meaning that, for example, if homotopy groups of X are finitely generated, we obtain the completion map. So the cohomology of the homology of the spectrum on the left is isomorphic to the homology of the spectrum on the right with FP coefficients. And additionally, this thing here is a P completion. So in the sense of both field localizations, for example. So the idea is that Adams Spectral Sequence recovers information about homotopy groups of some spectrum from the information about homology of the spectrum, and let's formulate how precisely this works. So assume that we have a morphism like this from X to the totalization of this post-simplicial ring spectrum. Then it is equivalent to homotopy limit of n-fold totalizations. And we have a canonical map from the homotopy limit to one stage of such totalization. And then we have a filtered object of homotopy groups of X, where the term number I in this filtration is given by the kernel of this map described here on homotopy groups. So among other things, this filtration is commensurate with the p-adic filtration, meaning that for any index j, we have an inclusion of this subgroup into this term of filtration, and also another index which contains another index I less than j, which contains this term of filtration. So in particular, it means that if we complete with respect to this filtration, we obtain the p-completion of homotopy groups. And also this means that, this means that the spectral sequence of this filtration abuts to quotients of this filtration on homotopy groups, which look like this. And yeah, as I said, if we take completion of homotopy groups with respect to this filtration, we obtain the p-adic completion. And the E1 term of this spectral sequence of a filtration can be computed using, well, the following. So first in the row number 0, we get the homology of X with coefficients in FP. And in the row number 1, we get homotopy groups of this tensor product. And in general, we get just homotopy groups of tensor product like this. So we can consider the following decomposition of this tensor product that we used to compute the first row of the first page. like this. And we can apply the functor of homotopy groups, and we see that this thing on the right actually just gives us the dual to the Stirrat algebra, because it's the FP homology of the FP Erlenberg methane spectrum. And then this means that the zero row is like this, and the first row is just the tensor product of homology with the dual of the tensor algebra over the ground field. And so, in general, the first page of the Adams spectral sequence can be recovered from the following construction. So assume that we have co-module over the dual to the Stirrat algebra. Then we can form a post-simplicial object like this. And its associated chain complex will be precisely the E1 term of the Adams spectral sequence. So if we take as such an object the homology of X with coefficients in FP, this, as I said, produces the first page. And how precisely do these post-simplicial maps work? Well, first of all, we have a map like this, which is induced by the Fourier homomorphism or Fourier map. So yeah, we have a map from two-fold tensor product to three-fold tensor product. And this induces a co-multiplication on the dual to the Stirrat algebra, which means that, well, first of all, it means that now we know how to take the structure maps in this post-simplicial object. But also it means that the spectrum of the dual to the Stirrat algebra actually has a group scheme structure over the spectrum of this Erlenberg methane thing. And to return back to these structure maps, if so this map is induced by the map like this on spectra, which also comes from the Fourier map. And this means that for an arbitrary co-module over a dual, we have I guess, co-chain complex, which, or chain complex, it depends on your grading conventions, which works like this. So we take V, then we map it to global sections over this group scheme, which is the spectrum over of the dual to the Stirrat algebra, of the sheaf, which is obtained like this, and so on. And then we see that the second page is just the X in the abelian category of co-modules over the dual to the Stirrat algebra. So and that's like this. So one gradient which is denoted by this dot is the gradient on X, and the second gradient is just the natural gradient on V. Okay, so now let's consider a particular case of prime 2, and we can consider Xn, which is the internal home in the category of spectra between the suspension spectrum of RPM and the sphere spectrum. Then homology of Xn with coefficients in F2 is the same as cohomology with coefficients in F2 of RPM, which is precisely the ring of truncated polynomials with generator in degree 1 over the field F2. Now we have an action of this group scheme on the co-limit of spectra of these rings of truncated polynomials, which is precisely the, well, you can take it as a definition of the formal spectrum of the ring of power series in one variable over F2. Now, the Segre map, which we use to define the tensor product of vector bundles, or with line bundles to be precise, gives a formal group law structure on cohomology of RP infinity, which means that we have a structure of a formal group on the formal spectrum of the ring of power series. And this formal group law is just the usual additive one. So as we saw before, we have an action of this spectrum of the dual to the Steenrich algebra on the formal spectrum of the ring of power series. But since our action basically comes from topology, it should respect the structure of the formal group. And this means that this homomorphism into the group of all automorphisms of this formal spectrum as a formal scheme factors through a group of all automorphisms of this formal scheme as a formal group, which means that any element of our group G as it acts on this formal group should respect this addition law. And in particular, this means that we can present our elements of our group as a power series without the free coefficient, the free pi, because they must preserve this addition law. Now, the Milner's theorem asserts that the image of this group precisely coincides with the subgroup of invertible power series, invertible under composition, such that their coefficient in degree 0 is 1. So we always have t plus a1 t squared plus something else. And this fact works not only over p equal to 2, but over arbitrary primes. And in particular, this means that for any R, which is an F2 algebra, we have a representation like this of the elements of our group of points over R. So, yeah, group of points over R of the group scheme G. So now, the main technical goal of today's talk is to compute homotopy groups of NU. So in principle, we have some gadget that takes as an input something that we already know, i.e. homology of NU, and produces something that we want to get, i.e. homotopy groups of NU. Recall that homology of NU is indeed the rings of polynomials concentrated in even degrees. So the degree of BI is 2i. And that the spectrum of homology is the infinite dimensional affine space, over F2. Yeah. So an infinite dimensional affine space should be thought of as a colimit of a_n's as n tends to infinity. There are several possible ways to think of an infinite dimensional affine space, but we consider this one. And assume that we have a commutative algebra over F2 and a formal group law, which is just additive. Then our points of our points of the automorphism group of this formal group scheme preserving X up to the first order are precisely elements of our group of R points of G, but that was just said earlier. Okay, so rehashing what I just said, we have this description of G. And also we have a map between real and complex projective spaces. So the real space is mapped into the complex one via complexification. And on cohomologies, it is easy to see. This map is induced by squaring the generator of ring of the cohomology ring of the projective space. So this is a ring of polynomials over F2 with generator in degree 2. This is a ring of polynomials in over F2 with the generator in degree 1. And this just embeds into this ring, this ring by taking all polynomials generated by the square of the generator. And so this means that the action of this group scheme on the spectrum of cohomology of RP infinity transfers to the spectrum of cohomology of CP infinity over F2. Well, via the usual construction. So we have a map of rings, which means that we have a map of spectra in the other direction, and we have a transferred action. And the transferred action acts on. I guess I should rename the generators. So if we apply the element of our group to a generator in cohomology of CP infinity, we obtain the square of the same action on the generator in cohomology of RP infinity, and so this is just basically the same power series where we squared everything, because since we're working over F2, we don't have any binomial coefficients or anything like that, and this means that this formula works. So now let's denote by Z the spectrum of homology of mu with coefficients in F2. Then the action of G on this spectrum Z actually gives us the second page of the Adams spectral sequence. So in actuality, the second page is just the cohomology of the quotient stack with coefficients in the structure sheet. To see this, you basically just need to remember that what we do there is we compute cohomology of the group G with coefficients in cohomology of Z with coefficients in the structure sheaf of Z. So since this is just the ring of polynomials, we get what we want, and then this equality is just purely formal, basically. So the fact that cohomology of the group is equal to cohomology of the quotient stack is basically purely formal. And so our goal is to understand this quotient stack. So we want to understand something about the second page of Adams spectral sequence for mu, and we do this by investigating this quotient stack. Well, first of all, we have the Frobenius homomorphism, which goes from G to G, which we, to confuse everybody, denoted by G prime. And this homomorphism is not an isomorphism, obviously, and it has a kernel which we denote by K. as it turns out, action of G on Z, well, it's not hard to see from this description, factors through F, meaning that K is a global stabilizer of this action, and it acts trivially. So a first approximation of Z mod G is Z mod G prime. So yeah. And how Z mod G prime looks? Well, first of all, let's define another scheme, which we denote by Z sub 0. And it is a spectrum of the following strangely looking polynomial ring, where we only leave the generators which are not equal to powers of 2 minus 1. So obviously we have an inclusion of, an embedding of Z sub 0 into Z induced by the projection from the polynomial ring on all generators to the polynomial ring on some generators, which maps the generators in question to 0. So the action of G on Z determines an isomorphism. So G prime times Z sub 0 is actually isomorphic to Z. Or another sort of equivalent way to state this is that, well, it's not equivalent, but it follows that the composite map of this inclusion and this projection is actually an isomorphism of schemes. Okay, so let's try to sort of prove this proposition. Assume that we have an algebra over F2. Then alpha induces a bijection on, well, at least this is enough to show that alpha induces a bijection between R points of this product and R points of this scheme Z. Then if we do this for all R's, we will show this result for, we will show this isomorphism. Well, this isomorphism is equivalent to the fact that for any H on the right, there is a unique decomposition of H as a composition of F and G. This is a purely algebraic fact that if we have two polynomials and we take their composition, then we actually can solve the equations back and get the coefficients of these polynomials. So this is not a completely rigorous proof, but if you like play around a bit with compositions of polynomials, you will see that if we use these A's and B's as indeterminacies, then you can recover them from the coefficients of the resulting polynomial H. So this is a pretty standard exercise when you try to, like, I don't know, find some inverse in cohomology rings, then you usually do something very similar. Okay, so assuming that we've proved this isomorphism between G times Z sub 0, we can now see that we have an isomorphism like this. So this quotient step is isomorphic to first the quotient step of Z mod K, and then we mod out by the quotient of G mod K, so of G over K, i.e. G prime. And since the action of K on Z is trivial, this quotient, well, the quotient step, is isomorphic just to the product. So the usual fact that if you have a trivial action, then to get the quotient step, you need to take the product of the initial stack with the classifying space. Then you take the quotient by G prime, which obviously only acts on the left factor, which means that we have well, a composite like this. And this implies that the quotient is actually just z sub 0 times bk. This now allows us to apply the Q-naught isomorphism, which implies that the cohomology of this quotient stack with coefficients in the structure sheaf is the tensor product of cohomology of z sub 0 with coefficients in the pullback sheaf, which is the structure sheaf of z sub 0, and the cohomology of K with coefficients in F2. But since, as we know, on affine schemes, cohomology of sheaves in vanishes in higher degrees, we only get the cohomology in degree 0, which coincides with global sections, which are precisely this ring of polynomials. And so to compute the second page of the Adams spectral sequence, we only need to understand how the cohomology of K works. And this can be done relatively easily. So let's first of all understand how K works. So for any F2 algebra R, R points of K are presented by polynomials like this with an additional requirement that the square of each coefficient is 0. So the composition in this group scheme is very simple. We just sum up the coefficients of two series, which immediately implies that actually a K can be presented as an infinite direct product of group schemes of the following form. So spectral of the ring of truncated polynomials where truncation is done in the square of the generator. And this means that, not this, but also we have an isomorphism of coalgebras, not algebras, but coalgebras, where on the left we have the usual coalgebraic structure, which is induced from polynomial algebra, and it is preserved by truncation. And on the right we have the coalgebraic structure, which is induced by the fact that we have the group multiplication, which immediately induces the coalgebraic structure on the ring of F2 functions on this group. In particular, this means that cohomology or X in the category of comodules over this coalgebra can be computed in the category of comodules over this coalgebra, which immediately implies that the cohomology of alpha 2, which is equal to this X, I guess, yes, this would be more appropriate, is actually equal to cohomology of Z2 with coefficients in F2, which is, as we know, is equal to just the ring of polynomials generated in degree 1. So cohomology of K with coefficients in F2 is isomorphic, at least with some grading to the ring of polynomials where each generator has degree 1. But actually, this ring is bigraded, and the second gradient comes from the requirement that the degree of such a series should be equal to -1. And since the degree of X is necessarily -1 itself, this means that the degree of AI is equal to the power of I -1. And now we can use this isomorphism that we saw earlier so this one, to see that the second page of the Adams spectral sequence for a mu over in characteristic 2 is equal to the following ring of polynomials generated by the following generators with by degrees 2i 0 and 2j minus 1 1. So 2i 0 is for I which is not equal to 2j minus 1, and well, for the ones which are equal, we take the by degree to be this. And this immediately implies that since all elements, all non-trivial elements of the second page are concentrated in even degrees, the Adams spectral sequence collapses. And this shows that over F2, homotopy groups of completion are can be filtered in a way that give us back the ring of polynomials. So actually, this result can be obtained over any ring over any prime. However, there some care should be taken to avoid these issues with non-commutative rings, but it's not really hard because you have this very mild case of non-commutativity. You have to consider super algebras instead of just regular commutative algebras, but it is still not very challenging. And using the similar arguments, we see that for p greater than 2, we also have an isomorphism between the second page and a ring of polynomials with generators with similar by degrees. And in particular, they are also concentrated in even degrees, meaning that spectral sequence also collapses. So now we can prove the equivalence theorem, which asserts that we have an isomorphism between the Lazard ring and the homotopy groups of mu. And first, we observe that over any prime, we have an isomorphism of graded algebras induced by some filtration on homotopy groups. Well, we know the Adams filtration, which give us we have these isomorphisms which give us the following elements in associated quotients of this associated graded algebra. So for sort of non-special indices, we have elements which belong to the zero component, and in for these special indices, we have elements which belong to the first graded component. Then we can consider the Lazard ring, where which is the ring of polynomials generated by elements in degrees 2i. And we can consider a homomorphism of rings which maps ui either to an element which represents ci in the zeros graded component, or an element which represents ci in the first graded component, depending on which value of I we have, either a special or non-special one. Then it is quite clear that phi is a morphism of graded filtered rings where R is filtered by total degree. So you just take, so this is sort of a standard filtration of a polynomial algebra by the powers of its augmentation ideal. You take just the submodule spanned by all polynomials of degrees higher than some. And by induction, this phi induces an isomorphism between quotients of the ring with respect to these two filtrations. And in particular, this means that if we complete both rings with respect to these filtrations, we obtain two isomorphic things, which so on the left we obtain a ring of polynomials over p-adic integers. And now we can formulate and prove Quillen's theorem, which asserts that actually we have an isomorphism theta induced by the complex orientation between the ring of, between the universal ring of Lazar and the homotopy groups of mu. So first of all, why is it injective? This is not hard to prove because we already have an injectivity and an isomorphism when we take the composite of theta and the Fourier homomorphism. So since homology of mu is just the ring of polynomials, and it's quite clear that elements of the Lazar ring, the generators of the Lazar ring, are mapped precisely to these distinguished generators in homology. We have an isomorphism of rings, so it's injective. We want to show that theta is actually surjective. To do this, we should first observe that by Lazar's theorem, the P completion of Lazar's ring is just the ring of polynomials with the same degrees of generators, but with coefficients in p-adic integers. So this means that after completion, theta becomes an isomorphism. Let's denote by I, H, and J sort of canonical augmentation ideals. So just the ideals that contain all polynomials of positive degrees. From the proof of Lazar's theorem, we know that we have an epimorphism between sort of cotangent spaces of L and of L hat and P mu hat. Okay, that's great and all, but also we know just by construction that if we take the quotient of the first power of I or H by the second power, we obtain something that is spanned as a linear space or a module by the generators. So in particular, in degree 2n, it is just a free module spanned by Tn or Un, if we consider homotopy groups of mu. And we know that theta of Tn is equal to lambda Un plus some decomposables. So actually what we need to show to see that theta is an epimorphism, we need to show that lambda is a p-adic unit. And we know that if we apply H, so the Fourier homomorphism to Un, we obtain lambda prime Bn plus some decomposables. And by Lazar's theorem, we know that we know that the composition either multiplies by p if the value of n is special or is 1. So in the second case, it is clear that lambda is a p-adic unit, and we basically constructed its inverse. And in the case of a special value of n, it is enough to show that lambda is divisible by p. Then we can divide both sides by p and see that it is also a p-adic unit. But this immediately follows from the fact that Un is contained in the first term of the Adams filtration on homotopy groups, and we saw that the Adams filtration is commensurate with the p-adic filtration, meaning that lambda is divisible by p. Okay. So this proves the Poulen's theorem, I guess, and I think that actually, surprisingly, that's all I wanted to say today. So there is, of course, this slight generalization of Adams spectral sequence called Adams spectral sequence, but I don't think that it is wise to cover it now. Maybe there are some questions, or I don't know. If no, then I think that we can stop the recording and
Let's thank Grigory again. So maybe I can stop the recording.
yeah, sure.